This is an interesting paper that I would like to discuss at least very shortly without getting into the details in this video specifically. And I'm talking about this article here titled Narrowband Systems and Gaussianity. It is important both in mathematics but also in engineering, especially when studying random signals and linear systems as well. It was written by a mathematician, quite well-known mathematician, and his name is this one, Papoulis. The surname and the name is Athanasios, something like that. It's Greek, so I don't know how to pronounce his name correctly, but never mind, so accept my pronunciation. And it was written in 1971, so it's quite old, and you can find it on the internet for free. Basically, it's very easy to find it. It's an interesting one, which I studied, I remember, in 2017, so several years ago while pursuing my PhD. And it was an important paper to read because the results that Papoulis wrote about, or let's say derived in this article, are frequently mentioned in the literature of vibration testing. So I have PhD related to vibration testing, vibration analysis, and in particular random vibration and fatigue, the relation between fatigue damage and vibratory signals, let's say. So I don't want to get into that here. I would just like to mention this result and try to let you understand at least the basic result derived in this article without getting into the technicalities here. So I would like to start a small series of lectures related to the derivations that are shown here because they are important in mathematics in particular. There are very interesting concepts related to random signals. So we have the theory of random variables and probabilities. So we have distributions, Gaussian distributions. We have correlations, how to calculate the expectation of a random variable, the variance, and other interesting mathematical concepts like, of course, the Fourier transform. So the Fourier transform is used in this article. The Fourier series is indirectly used in this article as well. And I think that the mathematical concepts are worth exploring. So I might decide to go through the derivations here because they are not carried out in full detail. So in 2017 I decided to do all the derivations, to go through all the derivations, to do the calculations. So I have my own notes that I wrote at that time, and I would like to go through the derivations because, as I said, in my opinion, it is worth exploring this article more in detail. But here I would just like to tell you the major result of this article. In particular, it's written in this page and also in the last pages of this article. And let me sketch, basically, in very simple words, what this article is about. So we can sketch a linear system which is characterized by a certain impulse response, which I will call h of t. So I am assuming some familiarity with linear systems. I will not get into the details of it here. H of t is a certain function which describes how the system reacts to an impulse. So it is the response of the system to an impulse. Then we might have some input signal x of t, and the system will, in this case, respond with a certain output y of t. And in particular, one can show that the output y of t is given by a convolution between the input x of t and the impulse response. So this is how the convolution is denoted with a star. You can rewrite this as an integral between these two functions, and I mean there is a product of these two functions. One of them is shifted by a certain amount, and then you integrate over some variable tau. But I will not write it here because it's not really fundamental. Papoulis is interested in analyzing, in particular, the distribution of the response, because in dealing with the random signals, such a signal here, the input is characterized by a certain distribution, and similarly we have a distribution of the output. And in this case we might assume for simplicity that the system is well known and there are no random variables hidden inside the function, the response function of the system. So we only have randomness in the input, and therefore, of course, there must be a randomness in the output as well, which depends on the randomness that we have on the input. But in principle, the distribution of the output will be different from the distribution of the input, and it depends also on the characteristics of the impulse response of the system. So we might have different realizations of this process. So this x of t might be associated to a process because it can be realized in different manners. For example, we might have a signal x1 of t, and then we might have another signal x2 of t. Under a certain amount of time, the signal will change, its time values. So we might have different time values, but if the system, if the input signal is stationary, then the distribution of these signals will be the same. So we might have another realization x of t of the same process. So this signal is associated to some randomness, because if we change our time interval in which we observe the process, we see different signals. So if we assume that we observe the process from 0 to capital T, which is the duration, the signal might be realized in a certain manner, for example like this, or we might have a different vibration. For example, this might be x1, this might be x2, from the same initial time 0 to the same final time capital T. And similarly, we might have a different realization x3 where the signal is different. But if we study the distribution of such signals, we find the same distribution, assuming that the process is stationary, meaning that the distribution is the same, basically. But the distribution of the signals that we have in the output, for example, the response to x1 will be some function y1 of t, similarly the response to x2 will be y2 of t, and similarly the response to x3 will be y3 of t. These signals will be characterized by the same distribution. So of course I'm not getting into all the details behind the story because it would be a long story. I have said something in a course on vibration testing, but I will not repeat those concepts in here. So what's important is to study the distribution of the output and also of the input. And Papoulis does that. In particular, Papoulis is interested in studying the distribution of the output, which in this case is called f of y, where y is the output. And he wants to find a bound, and by bound it means that he wants to find an inequality which studies the difference between the distribution f of y and a Gaussian distribution g of y. So g is a distribution of a Gaussian process with zero mean and variance equal to 1 in particular. And I will not get into all the details here. For example, what a dependent process means. It is described here. You can try to understand it, but if I will go through the derivation, we will get back to that, of course. But anyway, he finds how to calculate the difference between the distribution of the process y and the Gaussian distribution g of y, and if this difference is very small, it means that the distribution f of y will be close to a Gaussian distribution. So under certain characteristics of the system, and in particular the important characteristic here, the important parameter is this w0 or w0, which is the bandwidth of the system. So if we calculate, for example, the Fourier transform of h of t, we can call it capital H of omega, and we can plot the mode of h of omega with respect to omega. And we might find, for example, something like this. We have some curve which goes to 0 outside of a certain boundary. For example, here we might have the maximum value at omega bar, and this point here where this function goes to 0, or almost to 0, let's say, is omega bar plus some omega 0. And we assume some symmetry with respect to this axis where the function is maximum, and therefore the value where the function goes to 0 here will be omega minus omega 0. Omega 0 is important because it tells us, so omega 0 would be this length here, and it tells us the interval in which the function is non-zero, or non-negligible, let's say. And that's proportional to the bandwidth of the system. So if we assume symmetry also with respect to the y-axis, we have the same curve here as well. And this is actually important if we assume that h of t is real, for example. So the mode of h of omega will be equal to the mode of h of minus omega. And this makes sure that h of t is real. But I will not get into this aspect here. And Papoulis found that if omega 0 goes to 0, so as we decrease the bandwidth of the system, and under certain assumptions which are quite technical that I will not get into, but it's quite general, let's say, we can say that the distribution of the system approaches the Gaussian distribution. So you can see that this omega 0 will go to 0, and therefore this difference will go closer and closer to 0. In particular, this inequality holds in the case of shot noise. So for shot noise, the input x of t will be a certain summation, let's say, of some coefficients that multiply Dirac deltas centered at t minus tn, where this tn here, these tn's, are the points where the Dirac deltas are located, and they are random variables. So we might use the tilde here to denote the fact that this tn is a random variable. So of course x will also be a random variable because there is randomness in the definition of this variable here. So we might also generalize the randomness by considering this as a random variable as well. So the coefficient as a random variable, for example, it depends. There might be different degrees of variability or if you want a randomness in a certain variable. So in this case, I'm assuming that the randomness is just in the points where the Dirac deltas are located, and one can show that the response will be of the following kind here. So in this case in particular, if I remember correctly in the derivation, so I will not go into the details here, so it's not really important, but these coefficients are set equal to 1. So we just have a sum over n of these Dirac deltas. But for a more general input, so if the input is more general, it is still a random variable, a random function if you want, because it depends on time, but it is more general in the sense that it is not written as the sum of Dirac deltas, then we have a different inequality, and the inequality is of the following kind. So it is similar. You can see that the variable here changes. So we have sigma 0 in the argument of the Gaussian distribution, which gives the possibility of having a variable with its variance not necessarily equal to 1. So it's a generalization. And you can see that in this case the dependence on omega 0 contains a square root here, and also a power 1 over 7, because we have root 7 here as well. So all in all, if you have root 7 and then you have root omega 0, this would be omega 0 to the power 1/2 to the power 1 over 7, so this would be omega 0 to the power 1 over 14. And well, you can see that even if omega 0 is quite small, this exponent here will smoothen it out, so it will not go to 0 too rapidly. In particular, if I calculate this value here, I don't know how many zeros are there, but it's a very small number to the power 1 over 14, you can see that you still get 0.1. So it's still small, but not as small as this value here. So you can see that it will go to 0 not so fast due to the exponent there. So the bandwidth of the system must be very, very small, so that we can say that the distribution will go to Gaussian, to the Gaussian distribution. And anyway, there are some technicalities that I did not touch, so there's more to it than meets the eye, and if possible, I will go through the derivations. In particular, I will start from the results in the appendix, and of course you have to be aware that the results are quite mathematical, and sometimes you might also lose some intuition behind them. But in this case, I would like to focus on the mathematics, and step by step, if you have some basic knowledge about random variables and calculus, I think that you can follow the derivations here. You might as well read the article, but of course you still need a pencil or a pen and a sheet of paper, because you need to write down the formulas in order to really understand what's written there, because it's very mathematical, and the mathematics is not too advanced, in my opinion, if you have some basic prerequisites in calculus, in probability and random variables. So of course I say basic, but this depends on your specific preparation, of course, and anyway, with the basic courses on such concepts, you should at least be able to grasp the essence of this paper. And as I said at the beginning of the video, this paper is actually important in engineering, and not just in mechanical engineering as it was for me, but also in other branches, in signal processing, of course, and others, where you have signals and you are interested in the distribution of these signals, and you want to understand whether the distribution will be Gaussian if we consider the response of a certain linear system. And I would say that's it for this video.